air enters a constant area heater at Mach 0.5 with a total pressure of 200 psia and a total temperature of 100 Brankenes. A heat transfer of 100 BTU per pound mass into the air inside the system occurs. Determine the Mach number, total pressure, and total temperature after the heat interaction. Assume a gamma of 1.4, that's the specific heat ratio. Ratio of specific heats. And CP, that is, I don't remember. I remember there's a CP and a CV. I can't think of the word right now. Shown on a TS diagram. This is going to be CP because there is mass flow. Okay, I can't think of the word right now. So let's draw something about it. So what's happening? We've got a constant area heater. So we've got some form of heat coming in here. We'll call this Q dot because it's a rate. And determine the Mach number. Well, we have a Mach 1 in here. They also tell us a pressure one total, so we should include that, PT1, and they tell us a total temperature, TT1. Determine the total pressure, total temperature. So after, we want a Mach 2, a PT2, and a TT2 right here. And this is open, so I'm going to make this like that. There you go. Now, what am I going to do? We're going to write the assumptions here. So what are the assumptions? Well, CPG, because we see gamma. And then we have 1D flow, because we're summarizing the whole cross-sectional area of the flow with a single number per each property. Steady, and that's going to turn out to be very useful. CISO, that's also going to be very useful. And single in, single out, steady, 1D, CPG, and what else? Am I forgetting something? It's not adiabatic, but we're assuming it's isentropic. Isentropic, which essentially means that if we look at our delta S, we get going from 1 to 2. Sorry, we're not assuming it's isentropic. We're assuming it's reversible. You can't, because if you say you're isentropic, you're saying you're both adiabatic and reversible. I just want it to be reversible because we're saying that there's a change in Q over T, but this S gen is 0. Okay? Those are the irreversibilities. That term accounts for irreversibilities. So how do we do this? Well, we go to the supplemental data pack, and I want to show you the rate version of the second law, of the first law of thermodynamics. So that's going to be over here. And if we go up to our equations, we notice we start to have all of these equations, right? And here we have the first law of thermodynamics, which is this one right here. And then we notice also that we have something interesting here. The total enthalpy definition. And then we have, what else? I think there was gamma, which is CP over CV. So one is a I can't think of this word. It's bugging me. Okay, I'll think about it. So we're gonna use that equation. So actually, why don't I take a screenshot of it, since it's kind of long, or I can just remember it. The change in energy of the control volume divided by time is gonna be equal to all the stuff coming in minus all the stuff coming out. So if I remember it correctly, then this should be the solve. It's going to be the change in all the energy coming in with respect to time is going to be equal to the work dot in plus the Q dot in plus the M dot in times the summation. Let me do that better. Times the summation of static enthalpy, which I don't remember how it's written, just H. H in plus V squared in over 2 plus G Z in, that looks like an M, G Z in, and then what? Minus the same term, but everything is gonna come out. So the subscripts is gonna be out. So I'm gonna just copy it and paste it over. It's not allowing me to do it. Come on. Copy, paste. Now you have to remember to put a parenthesis in here, otherwise only the first term would be subtracted. And that's it. And then we go on with our assumptions, remembering that this is total enthalpy. This is HT2, 1 and 2. So to put subscript 1 and 2, we use the assumption of 1D flow. And then we're saying if it's steady, and this is going to be 0, so that means we're steady. And we're saying that there is no work in, no work going out. There's Q in, but there's no Q out. So I'm getting confused by the subscripts here because I forgot to change them. This is out, out, out. So, and these are also out and out. So what we do now is there's no Q out, and this is going to be the same for both. That comes from CISO, so let me just use a different color, and that's going to reflect this idea right here. And then we're assuming negligible potential energy effects, so I'll add that. Negligible PE, potential energy. And that's, I'm going to underline that in green, and that's going to be this guy and this guy. So what do we end up with? Well, we end up with 0 is equal, oh, and the summation is also part of the CISO. So that's going to also go away, because there's only one inlet and one outlet. So Q in plus H1, I'll call it, total. So H total 1 minus H total 2. So now what can we say? Oh, and I forgot to put the mass, which is the same, so we can factor it out. So M dot right there. So now we can say what? Well, we can say that Q in is equal to M dot times Well, this was a negative, or we can multiply both sides by negative and change the position of these two so that HT2 becomes positive and HT1 becomes negative. Now we can divide both sides by m dot, and what we get is this, and that is HT2 minus HT1. Now think about this. This is the same thing as the big Qn dt over an m mass dt, because the dot stands for derivative with respect to time. So if you do this, I know you can't really do this, but conceptually speaking, the time component goes away. And so what is a mass, what is a heat divided by mass is going to be specific heat. So it's going to be small q in with no rate. That's going to be HT2 minus HT1. And what they gave us was not a rate, right? They gave us BTU over pound mass. I think I did say that was a rate, but I meant to say it wasn't. So now we just need to go back to the supplemental data pack and remind ourselves of where the total enthalpy formula, or how that could be broken. And we see that it is this one right here, Cp times T2 minus T1. So we can say here that this is the same thing as Cp times T2 minus T1. Now they gave us T1, so we can solve for T2. And why do we want to solve for T2? Well, I'll show you in a second. So now we have Q in plus T1, Q in plus T1, no, sorry. First, see, that's what happens when you skip steps. Don't skip steps. So let's do it one step at a time. You want to divide by Cp, because I'm starting to free T2. So we get Q in over Cp. And that's going to be T2 minus T1. Then I want to add T1 to both sides. I'm going to flip the equal sign. And I'm going to get Q in over Cp plus T1 is going to be equal to T2. Now Q in, they told me, is 100 BTU over pound mass. So this is going to be 100 BTU over pound mass. And I want to divide this by 0. Or maybe it wasn't 0. Yeah, 0.24. And this one doesn't have any units. And I want to add it to T1, which they're telling me is a rankings. Where is it? 1,000 ranking. Plus 1,000. Plus 1,000 ranking. So how are we going to do that? Well, Cp, lucky for me, I made a mistake, has units, BTU over pound mass times ranking. BTU over pound mass times ranking, which is going to make this turn out into 1 over ranking, which is not what we want, which is suggesting that we made maybe an algebraic mistake somewhere. So let's see. Cp over Q in, go back to this, we see to free P2, we have change in H2 minus H1, which we said is Q, small q. So no, we didn't make any algebraic mistake because we were doing steps one at a time. So given that we didn't make any mistakes, how is it possible that the units are not working out? Perhaps I wrote this wrong and the ranking should be here. And is my theory correct? It is. So now we know that we didn't do anything wrong. It's always good to check. Now we do 100 divided by 0.24, and now we add 1,000. And what we get is 1,416.7. 1,416.7 ranking. I wonder if that's what we were supposed to get. Yes. And we can do the same for the total. Well, actually, what we can do is we can find the Mach number, because we can say M2 is going to be from the supplemental data pack. Supplemental data pack is a function of the T2 over T total at 2, which we are saying that and do we know the T total at 2? Let's look over here. So if we go to the supplemental data pack, for after the oblique shock chart, we're gonna see we have these things, not Fano flow, we're doing Rayleigh, and we have to extend it to the choked flow. So what we're gonna do is we're gonna say, do we have an M1? I think they gave us an M1, and M1 Mach 1 is 0.5. So this is what we're gonna have to do. Kind of like what we did earlier. We're gonna have to do 0.5. We're gonna have to start from the ratio that we want, which is P2 over P star. P2 over P star. Times P star over P1 times P1. Now, I see a problem here. The problem is that I don't have this. This is a function of the Mach 2. So to find the Mach 2, I need to find some other way to do it. And if I look at the relationships that I have available, I have the total temperature over T total star for Mach 1. I don't have it for Mach 2. But I can find TT star, which is then going to help me out, right? So what I can do is I can say, okay, well, T star for 1 is going to be the same as TT star for 2, because of that continuity idea that I showed you in the earlier video. And so what is this going to be? Well, this is going to be TT star over TT1 times TT1. And they gave us TT1. They told us that TT1 is, what is it? 200 psi. So what we're going to do, this, remind ourselves, is a function of the Mach at 1. So this is going to be 200 psia, and this is going to multiply. The initial Mach is 0.5, so we go to 0.5, and we see that that is 0.6914. So this is 0.69, I don't know why I did pressure, 0.6914. We need to flip it. This should be temperature. The initial temperature was 1,000 degrees rankings. So we find the total temperature for the flow choked, 0.6914 to the negative 1 multiplied by 1,000. Oh, I didn't get a calculator for that. Well, actually, because it's in the denominator, I might 1443. So 1446.3 rankings. And now we can say, we can find the Mach 2 is a function of T T2 over TT star. So a function of what? Well, TT star we just calculated. And the other one is 1416.7. They're both rankings. So let's do 1416.7 divided by 1446.3. That gives us 0.9795. So this is a function of 0.97995. And so then we go back to the supplemental data pack and we look for this ratio and we get 0.9797, about 0.84. So this is about equal to 0.84. And now that we have this Mach 2, we can find this guy, and we have this guy from Mach 1, because that's a function of Mach 1. We just have to remember to flip it, and we have P1 total. So I have to change the subscript to P total at 2, P total 2, P total, this is P total 1, P total 1, P total. Okay, so let's do that. From 0.84, we want the pressure over the total, so that's the last column. 0.84 is going to be 1.0124. So 1.0124 multiplied by, now we're going to look at Mach 0.5, 1.1141, 1.1141. Remember to flip it. Now the total pressure at the beginning was 200 psi. So that's going to be 1.0124 multiplied by 1.1141 to the negative 1 multiplied by 200. And what we get is 181.7. So that's 181.7. Now, does it make sense that the total pressure went down? Well, they're asking us to show on a TS diagram. And we're saying that the total temperature went down. I don't know how I'm going to justify that, because to me, it's a little bit non-intuitive, I guess, because if we're putting heat in the system, I would expect the total temperature to go up because it's not adiabatic anymore. I know it's the entropy goes up, so we're going to the right. The static temperature we haven't looked at, but I know it's going to have this shape, so I'm going to kind of cheat, and then I'm going to have to understand better what's going on. So I know we're going to go from T1 to T2. P2 is going to change from P1. And now I would say this will not be the same. So let me go back to my notes so that I give you proper information. And if I look at the graph here, we see the PT1, PT2 change as well as we move through the Rayleigh line. We're going to see that the total temperature increases. And we're going to see that the total pressure decreases. Okay, so there's two things there. Total pressure decreases, total temperature increases. And I was mixing up the two. So if I go back here, I'm going to have PT2. That's going to be less than, let me move this line. So trying to draw, okay. PT1 is going to be here. PT2 is going to be over here. And the temperature should be higher at T2 than it is at T1. This is good. This is how you learn. So P1, P2, PT1, PT2 is going to move to the right. The temperature is going to go up. And so I'd have to draw it like this. But the static temperature goes down. That's interesting because the flow is speeding up and the heat cannot catch up with the fact that the speed of the flow. So what we get is that this is actually not the way I should draw it. Let me make it a little bit neater. And I know maybe this part for you is a little bit tedious, but it's very important for your understanding. So if this is TT1, TT2 must be higher because we added heat to the overall system. And so this is going to be my PT2. This is my PT1 right here. So as we move to the right, the total pressure went down. So that checks out, and the total temperature goes up. So that also checks out. Okay, so this would be the graph that I would do. I hope this was useful, and good luck.